Hey guys, I'm Jon Bratseth. I'm the architect of Vespa, which is what we call a big data serving engine. That's obviously open source. I'll get to the connection to Hadoop in a while, but first let me try to place this technology in the landscape of big data technologies by looking at how companies mature to use big data. First, companies are producing data, but they're not really using it systematically. Honestly, that's where most companies are still at, which is what I call the latent stage. Then they get to the point where they start using the data for manual decision-making by humans, generating reports and insights and so on that influences the decisions that people are making. At some point, you want to start using your data to do automatic decision-making, that is learning or AI. So that's the next level, level 3. And on level 2 and 3 is most of the big data technologies that we are used to, right? Like Hadoop and Spark and all of those things, right? But at some point, you want to take your decision-making further and make decisions in real time while your users are doing some action, right? Real-time decision-making. And that's where Vespa comes in. So there's 2 times, yeah. Yeah, so let me use an example, which is classical example is if you have a recommendation service like a movie recommendation site, right? If you're at the first level, you're not really doing any systematic recommendation to users at all. If you are on the analysis stage, you have editors that create recommendations for young people in America or whatnot that they can come up with, right? At level 2, you actually compute list of recommended movies for different kinds of users automatically. And then you take these computed lists that you compute every day or whatever and ship them to some serving system that will statically serve them, right? Once you move beyond that is to compute the list of recommendations for a given user at the point in time when the user needs the recommendations, right? Yeah. That's the third step, yeah. Okay, so there's 2 types of real-time decision-making, right? One is where you can make your decisions over a single data point. That's it's either, if it's a data stream, that's the typical streaming application, or if it's a request response kind of system where you can make a decision based on one data point, then it's usually nowadays called model serving, right? That's sort of an easy problem. The harder problem is if you need to look at lots of data points to make a decision, but you still need to do it in real time, right? And the recommendation is a good use case because you can't just pick one movie and compute whether it's good for this user, right? You need to look at all the movies in your catalog and compute a score for that user for all the movies and then sort the list and return it to the user. So that kind of thing. So that's the problem that Vespa solves for you, doing that type of operation in real time. So what do we need to do that? We need obviously real-time serving. It needs to be truly real-time. So we need response times in typically less than 100 milliseconds because we know that end users get annoyed if things start taking more than about 400 milliseconds, and you need to set aside time for returning the response to the user front ends and whatnot. So typically the budget for the backend systems becomes somewhat less than 100 milliseconds. Since you're making decisions in real time, we typically need the data to be up to date as well. That's part of the point, right? Part of the benefit of moving the decision making to real time is that you can use data that is up to date, but that obviously only works if you can also write data at a high throughput rate while you are serving with the system. Hopefully you will have lots of users, and because it's big data, it's lots of data, so you need to be able to scale to large amount of traffic and lots of data. And because we are dealing directly with end users, it needs to be always available. So we need to be able to recover from hardware failures without any manual user intervention. The system needs to keep working if you're losing nodes and things like that. And for the same reason, we need to be able to change the system while we are serving. So change the schemas, change the logic components, change the machine learn models that we have learned, and so on, while we are serving and handling the write traffic. Finally, because this is just part of the big data stack, it needs to integrate with Hadoop for data streams, in tools like TensorFlow and so on for machine learn models and so on. So, well, yeah. It does both of it, but not by fetching the data and sending it somewhere and then making inferences, but doing inferences where you store the data, which I'll get back to. Yeah, that's part of the point, because otherwise you can't scale. Okay, so Vespa is a platform that solves these problems for you. It actually has a fairly interesting genesis story. It comes from a search group at Yahoo, which did web search, which also did most of the early development on Hadoop. Actually, Vespa is slightly older than Hadoop. Both systems uses the same strategy to scale to large amount of data, which is move the computation to the data rather than the other way around. So use the same thing in both systems. And since you open sourced it about a year ago, you can have access to all these features if you like, and you can find it on vespa.ai. I talked about recommendation. That's sort of a canonical use case for this, but the original canonical use case obviously is search, and specifically web search and other large corpuses that are used directly by consumers. And the reason for that is in those systems, you can't really pre-compute all the things you want to show to users, right? Because there are just so many potential queries that you need to compute the responses to the queries in real time. And that involves both finding the subset of data that could be relevant to the user and compute some machine learn model to find a final result that you want to return to the user. So that was a really hard problem to solve at that scale. But luckily, since web search was very economically valuable, we had the funding to solve these problems, and that's why we have systems like Hadoop and Vespa. So a few words on how we use it in Yahoo. So Vespa is used for about 160 different use cases in the company. Some I could mention is each time you visit yahoo.com or one of the apps we have like news and finance and so on, you see articles, and those articles are computed based on your personalized profile on the fly by Vespa, both computed and served by Vespa. Same with the streaming ads that are in these streams. They are also computed on the fly by Vespa. And there we need to take up-to-date bidding information and so on into account as well, which is an interesting technical problem. So some more details on what Vespa does. It does unstructured text search, obviously, which is the original use case, and it does structured search in structured data. And you can combine both in the same queries to specify what you want matched to your query. It does relevance scoring, natural language, advanced machine learning models like deep neural nets and whatnot based on TensorMat. It also has support for organizing all the data that matches your query in real time and aggregating values or the data and so on. So you can do fancy visualizations and things like that. And you can do this while you do real-time writes at a high sustained rate. Typically, we can get a couple of thousand, typically like about 10,000 writes per node per second. The clusters are elastic and auto-recovering. So if we want to add capacity or remove capacity, or if we lose nodes, then the data will automatically rebalance over the capacity you have available without disrupting any queries or write traffic. On top of this, you also have a stateless Java container, so applications can add their own business logic that runs close to the data, because that's a very common thing you want to do. And because these clusters typically have many nodes and many processes and so on, they are managed clusters, so you don't set up the clusters yourself. You specify to Vespa what you want to run, and Vespa will run the clusters or the system for you. Yeah, so this is just some nice quotes from another company that has gone all in on Vespa. They are using Vespa for both search in their mobile app and recommendation of content and type ahead query suggestions as well. So that's they their 3 use cases. They picked up Vespa. I have a slide on them because they picked up Vespa a month after we open sourced it and so on, and then went all in with it. And now all the real-time stuff in production is based on Vespa. So what's Vespa similar to out there in the industry? The most similar thing out there is probably Elasticsearch. They're focusing more on analytics, which is kind of different from big data serving, which I'll get back to. Solar is also somewhat overlapping because they do search, but it's more geared toward enterprise search. When we get to relational databases and so on, the similarity becomes smaller. Right? So a few more words on Elasticsearch, because it's most of the users that we see today that are big, that have projects around Vespa, have it because they use Elasticsearch today and are not happy with it. And the 2 reasons they are not happy is because it's hard to do real-time writes at scale with Elastic. So they typically need to set up something on the side manually for the real-time writes, and then have some process to move data over and so on, which gets complicated, and all that you avoid with Vespa. And the other advantage we have on that these kind of customers typically like is the machine learned integration, that you can run TensorFlow models and so on natively inside Vespa. And obviously this is because Elasticsearch has different priorities. They are more geared towards analytics, which is a different use case. Some more details on that. When you do what I call real-time serving, as I mentioned, the typical latencies are below 100 milliseconds. While if you're doing analytics, your users are typically people that you pay to do some kind of analysis, right? And since you're paying them, then you can tolerate somewhat higher latencies. So the typical latency targets for these applications is 1 or a few seconds for queries to complete. And for the same reason, they have lower query rate than Vespa has. Also with analytics, you typically look at time series data where you don't ever change events that happened earlier, right? While with Vespa, we assume that the data is random write, and that makes some optimizations not available for us. And the other thing is Vespa has much more focus on high availability than the typical analytics use cases. So Vespa is, I would say, better in all these respects, but the flip side of that is that if you have data sizes in the trillions of documents, then Vespa becomes much more expensive that you can achieve with something like Elasticsearch. So overview of the architecture of Vespa. Vespa is a 2-tier system. There's a stateless Java container, as I mentioned on top, that handles all the incoming write traffic and query traffic and so on, and hosts both the global logic that lives inside Vespa and is part of Vespa, and where applications can add their own logic to process queries and results and so on. Below that, we have what we call content clusters that actually stores the raw data and maintain reverse indices, evaluates machine learned models, and so on. And that part of Vespa is all written in C++ because it's data near and it's mostly concerned with maintaining a lot of data in memory. And C++ is better for that, especially when you get to processes that are really large. Lastly, because we can have, yeah, you have a question? Yeah, there's no specific node requirement. You can run the whole thing, all the clusters, a complete system on a single node if you like. So you can run it in Docker on your laptop. If you want redundancy, obviously you need 3 nodes because you want to be able to do lead re-election as well. Yeah, so you can have any number of these clusters, and they can have up to about 1,000 nodes in the largest applications. Because of that, it's a lot to configure and set up, so users don't do that themselves. That is done by Vespa, by the third cluster type, which is the administration cluster. So what the users are configuring is what we call an application package, which is a much more abstracted description of the system that you want to run, that describes the clusters that you want and what features they should have and so on. And it also contains the components you want to run, the machine learned models you want to run, the schemas, your data, and so on. You deploy that to the administration subsystem Vespa, which will then set up the system for you. If you want to change your application, you just make the change to the application package and deploy again, and Vespa will carry out the change without disrupting any of the query or write traffic. So that's how it works on a high level. Yeah, on this, typically when we run Vespa in production, we run it in Docker containers, but you don't need to do that So on this level, it's just Linux nodes, and we don't really, there's no assumptions about that on this level. It's just a Linux node that needs to have an IP number and a host name, and that's it. So yeah, we persist the data, yes. Yeah, I'll get back to that in more detail. Yeah, but it's definitely a stateful system. You write the data to Vespa, and it's stored in Vespa in multiple copies, and we also have disk-backed indices and so on. So most of the point of Vespa is to be able to return responses with really low latency, regardless of the amount of data, the amount of queries, the complexity of our machine learning models, and so on. So how do we achieve that? There's three main strategies, which are quite obvious. The first one is parallelization. When you receive a query to the container level, the container will scatter it over all the data partitions that stores some part of the data that is relevant for the query. And all these partitions will execute their part of the query in parallel. On each of the nodes, it will also scatter over multiple cores at the same time. That will execute parts of the query in parallel in multiple threads. Right. Secondly, we move as much execution to these data partitions as possible. So one of the things we move there is evaluation of machine learning models. So when you have machine learning models in Vespa, you put them in the application package and you deploy. And when you deploy, Vespa will copy them to all the data partition nodes so that they can be executed locally, evaluated locally over the data that is stored on that node. And because of that, we don't run into any bandwidth bottlenecks when we want to evaluate a model quickly over many data points, right? Because we don't need to collect all the data and send it somewhere for evaluation. We do it in parallel on all the content nodes. And lastly, after all, this is a search engine in its core, and we are doing things like reverse text indices, posting lists, B trees, and so on for creating data structures that allows us to look up data fast at query time. So a few graphs here to get through the point of distributing the models to the content nodes. So this is from a test we did where we compared to the use case where we want to use to evaluate a machine learning model, a neural net that is trained in TensorFlow and using either Vespa or TensorFlow serving. So in the yellow line, we use TensorFlow serving inside these containers and got all the data from all the data partitions and put it in a single matrix for maximum efficient evaluation in TensorFlow, because it likes to see all the data in a matrix at once rather than one data point at a time. And then you can get decent performance when you have a single node, but it doesn't scale because even if you have a 10 gig network, you run out of bandwidth really fast when you have a lot of queries and a lot of data points you want to evaluate. While with Vespa, if you add more and more nodes, as we do on the x-axis, your latency keeps going down, right? Because you can do more and more in parallel and you never run out of bandwidth. Viewed another way, if you add partitions on the x-axis, you can evaluate over linearly more data points, or at least very close to linearly, while with something like TensorFlow serving, where you need to send the data somewhere, you end up hitting the bandwidth barrier and you won't get any more performance, even if you have more data nodes. So I mentioned the framework we have in Vespa for doing inference or machine learning models. So it's a tensor-based framework where we have a model of tensors and we have some tensor mathematical expressions. So we can write mathematical expressions over these tensors, and that's what Vespa will evaluate. So a bit different from things like TensorFlow where they have a graph view, we have a mathematical expression view instead, but it's sort of the same. So you can write these expressions manually to do neural nets or vector and matrix models and whatnot. And that allows you to do all the things that people want to do that we know of, but it's still kind of inconvenient if you train your model in something like scikit or TensorFlow or something like that. You just want to save your model and deploy it. So earlier this year, we also provided support for that. So you can just save your models directly from these frameworks, either TensorFlow or some framework that supports ONNX, which is most of the other ones. Just save it to the application package and you can directly deploy it to Vespa. So here's an example where we have 3 different models, one TensorFlow model, one ONNX model, and one XGBoost model. If you save all those in the models directory in the application package, they will be available for use in Vespa. And here's a very simple mathematical expression that uses these models, just for illustration. So here's another example of a TensorFlow model on the left and the equivalent expression in Vespa's mathematical language on the right. So you can handwrite the thing on the right if you want, but you can also just save the models directly to Vespa. So when we evaluate models, we don't use something like TensorFlow serving. We don't integrate on the query serving path with TensorFlow. We use our own engine, which is optimized for evaluating our many data points quickly, which things like TensorFlow is not. Okay, so this was a quick overview of Vespa. I'll skip to some slides where we look more into detail about how it actually works. But first, if you want to check it out more, you can go to vespa.ai. There's a quick start there. You can run it on your laptop or on AWS if you like. There's also a tutorial that starts with some data from Kaggle, do the training and deployment on Vespa and so on to build a blog, search, and recommendation engine. Okay, so a few slides on practically how to use Vespa just to make it more concrete, and then I'll look more a bit on the underlying technology. So to use Vespa, you either install RPM packages or Docker images. We create new releases about 4 times a week that automatically roll out to production on all the systems that we run, at least, which is about 160 and a couple of 100,000 queries per second, and lots of different use cases and so on. So after a day or two, they are really well tested. All the nodes in Vespa have the same packages or the same image. They just have different roles in the application, and the role is decided by the administration subsystem of Vespa itself, right? So to start using Vespa on some nodes, you just get the Docker image or the RPM packages on a bunch of nodes, and you set one config variable which points to the configuration servers, and the rest is done by Vespa. You never manually configure the nodes that are part of your Vespa application. So the rest is done, as I mentioned, in application packages. So that contains all the application level configuration that describes how to take the Vespa platform as such into a working application. So you create your application package and you deploy it to Vespa through a command line command or a web service if you prefer. And then Vespa will carry out creating the system that is described in your application package. In most cases, if you change your application package, you can redeploy on the fly, and Vespa will carry out the changes without needing to restart anything. That includes schema changes and changes to Java components and machine learning models and so on. For some rare changes like changing port numbers and whatnot, that requires restarts, and then Vespa will tell you what you need to restart. So what goes in the application package, these 2 slides is a complete example of the files you need in an application package. So the services file describes the clusters that you want to run. In this case, you run a single stateless container cluster and a single content cluster. The container cluster here has a single node. It runs the search middleware and the document API that allows us to write documents to it. The content cluster points to the schemas that describes the data in this cluster and has a bunch of nodes as well. And then these nodes here are logical names that are mapped to physical host names in a different file. And lastly, we need the schemas that were mentioned in the content clusters. And in this case, it was only one. And the schema contains 2 main parts. One is the fields and how Vespa should treat each of these fields. And the other is what we call rank profiles, which is the thing you want to compute for each of these data points, right? So you can have many of these rank profiles that contains different mathematical expressions that you want to compute. So you can choose between them in the query. And these expressions can be simple expressions that you write here, or it can be, as I showed you earlier, a TensorFlow model or whatnot, or some complex tensor math or a GBDT tree or whatnot. So it can be either point to one of these things, or it can be a large expression that is in a different file or a set of functions that you call from here and whatnot. So with these 3 files, you have a full application package, and then you can deploy that through that command, and then you can post data either through a web service API or using our standalone Java client, which allows you to feed with high throughput. And then you can get the documents that you fed earlier, obviously remove them, update fields, and so on, and you can run queries. So that's in a nutshell how you use it. A few words about operations. All the components of Vespa are clusters, so there's no single points of failure. And as I mentioned, we do automatic failover and so on. For our company, we have a hosted service so users deploy their application to our hosted service that we run out of my team, and we have about half a head for doing operations for all of these thousands of nodes and 160 applications. So we are really into automating everything, so we don't need to do any manual operations whatsoever. Okay, so how does the lower level stuff in Vespa really work? So first, matching is a big part of what Vespa is doing, obviously. So matching consists of finding all the documents that matches a query, whether a query is a natural language text or a bunch of nested Boolean criterions or something more complicated like a WAND operator or whatnot. It's used for 2 things. If you're doing something more along the lines of traditional search, the point is to find the documents that are actually relevant at all to the query, right? If you're doing something like recommendation, then ideally you don't really want to do any matching at all, because you would just want to evaluate some machine learning model over all the data points. But with millions or billions of data points, that can become really expensive. You can do it with low latency in Vespa, just add enough nodes to run in parallel and it will work fine, but it may be too expensive to make sense. So another way to view the query is that you write a query to skip through your data and find the most promising data fast for evaluating your model, right? So this is on a high level how the execution actually happens. The queries comes into the stateless container node, which processes it and sends it to all the content partitions in parallel. That will do matching, and while it's doing the matching, it will evaluate your mathematical expression or machine learning model or whatever it is while it's doing the matching. And then you can also do a second phase of ranking, where you compute a more expensive model so that you can allocate more of your CPU towards the best candidates. If you have a really large data set and you have something like a deep neural net you want to evaluate as your model, then it may be too expensive to evaluate it for all the matches. So then you come up with a simple, cheap approximation to whatever the neural net is doing and uses that as your first phase ranking function that will find the most promising data points. And then you can evaluate those most promising data points with your full model. So that's a very typical thing to do that Vespa can do out of the box. Then we take all the matches to your query and group them, aggregate data, and so on as specified in the query, and finally return all of this upwards to the stateless tier. It will typically throw away some of the data and then fetch more information about the remaining data and then return it back to the end user. For those who know something about search, we do what's called document at a time evaluation. So that means when we do evaluation, we have all the information about a single document across all the fields of the document in memory in one thread at one time. That allows us to evaluate non-linear models or the data, right? Which is not how search engines used to do it back in the days, but it's how it's done now because you want non-linear evaluation. We have two kinds of indices. One is the traditional posting lists that are suitable for text data, but it's not that suitable for more structured data. There we use B trees that are more similar to what databases are doing, right? So that's what we call attributes. So on each of these nodes, we maintain these indices and attributes while you are executing your writes and executing your queries. And we also have a transaction log that we store the data in so that we can replay the same way as databases do if the node suddenly crashes, right? In addition to all of this, we also store the raw data of all the documents so that you can get back the same data that you put in, and also we use that same data for redistribution when we lose nodes or add capacity and so on, right? And then we have one instance of all of these things for every schema for each of the nodes in the cluster. Some more details on ranking. Ranking can be simple mathematical expressions over data from the query, data from the document, data from your application package, and what we call match features that are computed that you typically do for things like text search, where you want to take data from the query and data from the document and compute some feature that captures something about how well one matched the other, right? So there's a wide range of features like that as well. Yeah, so here are some examples. We have text match features, we have geodistance, time ranking, things like that. I'll skip this part because I only have 2 minutes left. So the other big part of ranking is the typical thing you want to do when you do machine learning models. Let me mention one more thing. For traditional text search, you usually do, when you do machine learning models, you usually do gradient boosted decision trees. And those don't need any of this tensor stuff or anything like that. It just needs to be able to execute forests or small decision trees really, really fast. So Vespa has lots of optimizations for doing that. That can be expressed as mathematical expression as well, just nested if functions with pluses in between them, and Vespa will recognize that expression shape and do special optimizations for those. But that doesn't work for things like neural nets and so on. There you want not functions over scalars, but functions over tensors. So Vespa has support for putting tensors, that is vectors, matrices, and higher level data structures in your documents and sending them to the query and putting them in the application package and so on, and then writing mathematical expressions over these tensors. So you can write these mathematical expressions by hand, which is often quite useful, but you can also just use the expressions that you get directly from TensorFlow and ONNX compatible tools like Scikit, PyTorch, a couple of others. These slides are public, by the way, if you want to look at it more. Yeah, I showed this as well. Yeah. So just to show that as well, here is our, as I mentioned, our framework or language for grouping and aggregation. Once you have all your matches across all the nodes, you may want to group the data and aggregate values, create subgroups and so on, and that's useful for things like diversity, collapsing, tag clouds, graphs, navigational tools, and all of these kind of things is examples of what you use this for. To do that in Vespa, you add to the query a kind of Lisp-like expression that takes in a list of all the matches to your query and then group them for each of the groups, do something, and so on. Obviously, when we execute it, we never actually have this list because that would be really inefficient, because then you would need to send all the partial lists somewhere to execute this thing. So this is a logical model, and when Vespa executes it, it recreates the logical equivalent to this without actually ever having this list available. Mostly we can do that accurately, but in some cases we use data sketches and so on to approximate what you would get from doing it accurately. Yeah, and we have a logic container on top, as I mentioned, based on Jetty that does dependency injection, configuration, or components, and so on for you. Okay, so I won't go into more detail than that. You can find all information, documentation, and so on vespa.ai. If you have any questions, you can find me afterwards, or maybe you can do 1 or 2 questions now if there are any. Yeah, so there's a simple web service API where you can put documents, remove documents, put individual fields or documents and so on. And if you want to use, that's really simple and nice to use. But if you want to write with really high throughput, it doesn't really work, right? So we have a standalone small Java library that you can use instead that will basically multiplex and do asynchronous writes for you. Yeah. So those are the 2 options you have. Yeah. So the stateless container part and the administration part is all Java, and the content tier is C++. Because that's data layer, it's all about managing data in memory and so on. So it doesn't really work to use, well, we could make it work, but we wouldn't get any benefit from Java because we can't put this data on the heap and do garbage collection and so on, because we would run into the same kind of problems that these other engines does. Yeah. You can send images because you can represent it as a vector or matrix, right? Yeah. Thanks, guys.